Okay, so here we go. Solving quadratic equations by graphing. So this is going to be another way, and we're not going to graph it by hand. We're going to just let the calculator do the graphing part, which you may like. I need to change this to the left. Okay, so next slide. So again, what does it mean for a polynomial to be quadratic? What is it that makes all three of these quadratic? They have the x squared, right? The x squared, x squared. Okay, now that's three different kinds of quadratics. When there's no equal sign, that's just an expression, right? Expressions are things that generally you learn to simplify. And with these, we learn to factor them. Or you have an equation. There's an equal sign. And if it's a standard form of a quadratic, it's set equal to 0. You know, what do we usually do with equations? We solve them, right? We try to find the variable, the value of the variable. Okay, a function, what's the difference between this equation and this equation? Right, you've got another variable there, right? So actually this is y. Since it's isolated for the y, you would say that y is a function of x, right? Now, you're not just going to get one answer. You can't solve that for like one value. But what you can do is you can substitute x values, calculate the y values, which gives you points, and you graph them, right? Now, the shape of the graph, let's see, I'm going to write this as a simplify. This is the solve, and this is the graph. Okay. Good. Okay. If you graph it, if you graph a quadratic, it has a shape. It's not a straight line anymore, right? A lot of students will look at that and say it kind of looks like a U, which is not a bad general description of what you're looking at there. But it's actually called a parabola. I thought I had that written on the side somewhere, right? Parabola. Parabola. I mean, and you may think it looks just kind of, you know, it's any old kind of U-ish kind of figure, but it's actually a very precise kind of figure. It's a figure you might actually use. Anybody have a satellite dish at home? Satellite dishes are parabolas, right? They're parabolas because parabolas have this characteristic, which is if you take a bunch of parallel rays and you shine it into the back of it there, it'll reflect it all to one common point in the middle, exactly to that point. So as long as you know, satellite sitting way off in space, sending its signal down, the back of the dish receives it, and then it reflects it to the focal point, called the focus. But if you have a satellite dish, there's always like a feeder horn right there, and that's what it's going to. If this shape wasn't exactly a parabola, it would not work. Yeah. Well, yeah, the next thing I was going to say is that the headlight of a car is the same way. The back of it is a parabola. So if you took this to be the shape of the headlight, at the focus now, it's the light source. And when the light source shines, it, you know, goes off at the sides and straight out. And so I imagine the bulb in there, maybe it's working the same kind of way, right? That there's some kind of reflectivity going on in there. So parabolas are very precise shapes. And you can bet whoever's making a satellite dish, you know, it's some machine shop somewhere, and they've got a parabola programmed into the back. Now, if you look at most satellite dishes, you would probably look at it and say, well, you know what, it doesn't quite look like it's exactly like that. But I think that they do get kind of fancy with their shapes, so that it, you know, the feeder horn like is not like exactly in the middle, but they have made it so it's conserving that property where everything that gets shined in the back is getting reflected to that one spot. Because I see a lot of those dishes, and clearly it's not like right in the middle. But that is what parabolas are for. Now let's see. Parabolas are symmetric. If you drew a line right through the middle of the parabola, it's a mirror image on one side as it is on the other. Right? So they're symmetric. The bottom of the U, the bottom of the parabola is called the vertex of the parabola. Right? We'll see, we end up seeing that word quite a bit. Right? Like most functions, you could have x-intercepts and y-intercepts. Right? X-intercepts means where does it cross the x-axis. The y-intercepts are where does it cross the y-axis. You know, those are just points. If you can see the graph, you should be able to just read it off the graph, like the y-intercept is -3. The x-intercepts, there's 2. With a quadratic, you can have 2. -1, +3. Now, x-intercepts have another name, which actually are used more than the term x-intercepts, and that's called zeros. The zeros of a function are the x-intercepts of the graph. So more than anything, one of the main points of this lesson is to keep that in mind. You know, what is a zero? It's an x-intercept of the graph. Because most of the time they're going to ask, that's the way they'll ask it. What are the zeros of this function? And so you go there. Now, if I was going to write the coordinates of those points, the x-intercept and the y-intercept, remember, okay, this is kind of important. I'm looking ahead a little bit to the 9-week test we're going to take in a couple weeks, and this comes up. Right, the y-intercept is -3. That means it is the point 0, -3. Right? Because what is the value of x on the y-axis? It's 0. So anytime you see that the x is 0, then the y value is the y-intercept. Okay, same thing up here with the x-intercepts. What are the coordinates of that point? -1, 0. In this case, it's the y that's 0. Right? You're not above, you're not below, you're right in the middle. What are the coordinates of that point? 3, 0. Right? So there's a couple of important things on this slide, right? The way that the x-intercepts and the y-intercepts are as points, and this term here is zeros. Those we should know. Okay. So to solve a quadratic equation by graphing, and in fact, this works for more than just quadratic equations. It'll work for cubic equations or logarithms or trigonometric functions, any of them. It will always work this way. So first, right, let's say I wanted to solve this equation right here. What we've done up till now, we always had to get everything on one side and 0 on the other, and you need to do the same thing here too. So how would I get 0 on one side of this equation? Subtract the 3. So I turn that into the equation. So now I want to find where this expression equals 0. So what you do is you're going to go to the y equals on your calculator. We all know where that button is, right? Y equals. And you're going to enter that expression, the x squared minus 2x minus 3. Julian, you doing this? Pick up a calculator. Yeah. Right? Put in x squared minus 2x minus 3. Okay? In fact, I'm going to do it here myself instead of just pointing you at that. Where is this? So, turn it on, clear, second plus 712. Right, y equals x squared minus 3x, minus 2x, minus 3. And then if you hit graph, we should see a parabola. And then what we're interested in are the x-intercepts. I think this is actually the problem we did on the last slide. Okay. So does everybody get that picture? Is anybody's picture like not the right, it's not exactly like that? If your screen is not exactly at that resolution, so your parabola doesn't look quite the same, then zoom 6. The zoom key is right in the middle on the top. Zoom 6. And that'll make it so we're all dealing with the same thing. Okay, next. Right, so the x-intercepts of the graph are the solutions of the equation. So sometimes you could look at that graph and just eyeball it and say, what does it look like? Or where is it crossing the x-axis? And what would we say? X equals, yeah, -1 there. And for right there, it looks like x equals positive 3. So sometimes, like I said, sometimes you'll be able to just look at the graph. The solutions are right there. Now, you notice that I put in the parentheses there. I got to change this. Dock bottom. Also, and this gets more confusing, the solutions to an equation are also sometimes called the roots of the equation. So actually, we're finding the x-intercepts, which we know are called zeros, and they're the solutions to the equations, which are also called roots. And so those four, they'll ask the same questions, but use one of those different terms. So if you can see the x-intercepts, then that can be your answer, and you can be done, right? Second, you could look in the table of values. But where's the table of values? Right. Second graph. And again, if you want to find the x-intercepts, then look for where y equals 0. Isn't that what we just said? If the y is 0, then that is the x-intercept. So right there, 0, -1, so that's one answer. And then the other one is 3. So if you're not sure, especially like if it's at the edge of the screen and you're counting those little lines, is that 8 or 9 or whatever, go to the table of values and just find it there. That'll tell you for sure where it's at. Now, there is one other way, which involves some calculator steps, which if you're not up to the task, then we won't show them. But I would imagine that some are going to say yes and some are going to say no. I'm going to show it for the one or two that are actually like, yeah, I'd kind of like to know how this works. So the first thing is, if you put the equation in there and you look at the graph, the first thing you ought to be able to tell us, how many solutions do you see there? Meaning, how many x-intercepts are there in this graph? There's 2, right? So if we want to use the calculator to find those 2 zeros, what we call zeros, then one at a time, we need to go after those zeros. So let's say I want to find where's the crossing the x-axis on the left, that one that's on the left. And you go second, and you hit the trace button. Now we've been up there before. Remember when we used the second trace before? Solving systems, right? Solving systems. So we would go second trace 5. This time, if you look, the number 2 option is 0. So if you want to find a 0 with the calculator, second trace 2. Right? So second trace 2. Now, it's going to ask us, just like it did when we were finding the intersection point, it would ask us first curve, second curve, and guess. This time it's going to ask us left bound, right bound, guess. By left bound, it wants you to put in an x value, which is to the left of where you think the 0 is. So, I mean, if we think it's around -1, then you could put in -3. It doesn't have to be just one number. Anything that's to the left of that, it'd be fine. So you could go, I'm going to enter in -3. And you can see when I do that, it sticks a triangle up there, right at -3. Okay, now it asks me the question for right bound. Yeah. Second trace 2. Okay, so enter -3. -3, enter. Okay. Now, you have another option. Instead of like entering the values, like -3, you could actually just use the arrow keys and move it so it's to the left. So for this time, I'm going to use the arrow key, right arrow, to move the cursor so that it goes somewhere in this area here. Because I need to have an x value which is to the right of the 0. Not to the right of this 0, but just to the right of this 0. So watch what happens if I cursor over. In fact, it might actually already be there. Okay, if I right arrow, can we see the cursor on the screen? Okay. So when you're happy with where the cursor is, okay. When you're happy with where the cursor is, just hit enter. So you see what it did? It popped that other triangle on the top. And now it's asking guess, which is like saying, if you're happy where you just put those 2 triangles, just hit enter. And I presume that we're happy with that. So we hit enter. And it jumps to the 0, and it gives us that point, -1, 0. Okay. So if I wanted to find the other 0, then I'd have to start over. Second, trace 2. Right? For the left bound, I'm going to move my cursor. How about there? That's just it's to the left of that 0. So I hit enter. And then I move it to the right with the arrow key. It's going above and to the right. And I hit enter. And then I hit enter. And it jumps to the 0. And if that's too many calculator steps for you, then just depend on looking at the graph and estimating or going to the table of values. You know, the thing about the table of values is that it only has x values. You know, the x values are all 0, 1, 2, 3. They're integers. What happens if it's a fraction? What if the 0 is in between 2 and 3? Then you need that third process to figure that one out. But sometimes you could just estimate that one too. Okay, so let's try this. So, solve by graphing. Again, what's the first step solving by graphing? Get everything on one side, 0 on the other. How am I going to do that with this problem? Right, x squared minus 2x equals 0. Okay, then what? Put it in the calculator, right? Y equals, clear that one, x squared minus 2x. X squared minus 2x. And then look at the graph. See if you can estimate. You need to wake up, right? See if you could estimate just by looking at that. What do you think the zeros are?
0.
0 is 1?
2.
And 2? Kind of looks like that. Confirm in the table of values. Second graph. So you go to the table of values and see where the y is 0, the x values are. Because you have, could you put in x squared minus 2x? No, graph. That's crazy. I would just clear the memory. Second plus 712. Try it again. Should work. Right? So notice in the table of values, when y is 0, then the answer is the x value. So we got 0 and 2. Two answers.
Yeah.
Okay, next. So try this one. Try that one. On your own, put that in the calculator, see if you can spy the zeros.
Okay, so it's already.
This is your you try. Chop chop. 0 and 2.
You said this already. No, we said it.
Okay? Try this one here and see if you can come up with those answers. Did it work?
Yeah, it did.
Okay.
Hold on.
Yeah. Did you do it? That's the last one. Okay, now try this one. What's that? No, this one's not going to have 0 for an answer. Let's see. X squared minus 6x plus 8. And you got... So where are those answers? What do you get? 2 and 4?
Yeah.
Right? So it should have looked like this. This one was already set equal to 0. Hunter. Take it off. Right? Y equals x squared minus 6x minus 6 minus 8 plus 8 plus 8. And I graph it. So what does it look like the zeros are? 2 and 4, right? Now we could have solved this easily enough by factoring, right? What are the factors of 8 that add up to negative 6? Minus 2, minus 4. So I mean, if you can't think of how to factor it, then graph it. Okay, next. Okay, solve by graphing. So I mean, what's different about this problem?
There's a 1.
You know, it's got the negative on one side. You know, if we were factoring this, I would definitely want us to have it starting with a positive x squared. But when you're graphing, it really doesn't matter. I mean, what would be the easiest way to make a 0 on one side? Subtract 1. What else could you do? You could actually like add x squared and subtract 2. You could move these terms over here. You know, you could do either one, right? If you do the 1, it's going to look like negative x squared plus 2x minus 1 equals 0. If you do the other, it'll be x squared minus 2x plus 1 equals 0. Right? Those would not be the same parabolas, but they will have the same zeros. So try to graph, put one of those in the calculator. In fact, some can do the first one and some can do the second one and see what the zeros are.
I did the first one.
You did the first one and you see a 0? So here's the first one. Negative x squared plus 2x minus 1. Graph. Okay? If you did this one here, right, you would have got this parabola. Does it have an x-intercept? You know, it has an x-intercept, but it doesn't have the same kind of look, because before the graph was going through the x-axis, but now it's actually just touches the x-axis, which happens sometimes.
So if the x is negative,
if that is negative, then it goes down, right? What would have happened if I graphed that one? I would have had a parabola that goes down, touches 1, and then goes back up. So it's not the same parabola, but it's the same 0. So it doesn't matter which way you do it. So it'd be a reflection across the x-axis. Yeah. Right. So, yeah, that is an x-intercept. Again, if you're not sure, look in the table of values. Second graph. See where it is you've got a y value that equals 0. And it looks like when x equals 1, y equals 0. So the answer is x equals 1. You know, if we would have factored like this one over here, that would have been x minus 1 squared equals 0. So the truth is that these are perfect square trinomials, and that's what you get with a perfect square trinomial. That it actually, the parabola will just touch in one spot and then go back on the same side. Okay, next. Solve by graphing. Okay, let's try this one. What do I need to do to this one? How? X squared minus 4x plus 7. Okay? Equals 0. Graph this one and let's see what it looks like. X squared minus 4x plus 7. And we graph it. And what do you notice? How many zeros do you see?
None.
How many x-intercepts? None. So there's no solution.
A lot, really?
Yeah, but we're not interested in y-intercepts. We're interested in x-intercepts. So when you get that kind of a graph, that means there's no solution. right? We can't deal with that in this class now. When you get into Algebra 2, we deal with that by creating a new kind of number, which is called imaginary numbers. But we can't do with that now. So when you just, bottom line, if you get that graph, no solution. Right? No x-intercepts means no solution. Okay, and next, there are some questions. There's some questions that are going to ask you to find the zeros, right? When you find the zeros, just means substitute the f of x, put a 0 there. And now you're doing the same thing. That's what it means to find the zeros. You would solve that equation right there. Again, we know that the zeros are the x-intercepts anyway. Okay? Forgot what they were going to say.
Excuse me, I need Kaylee Leslie for early dismissal.
Okay.
Oh, great. Thanks a lot, Millie.
And why did you